how to master the solution of a 10 degree from equation. Okay, let's say we present a 18 degree from equation, and we are going to solve it and find out the exact sum of it. Okay, so let's join the lecture and try to do it. Okay, please.
Those intimidating strings of S's raised to these dizzying powers. For the longest time, many of these mathematical beasts were considered fundamentally, well, out of reach for exact algebraic solutions.
And what's fascinating here, I think, is how often we, in the world of mathematics and science, we kind of find ourselves settling for approximations.
Right, the good enough answer.
Exactly, especially when complexity scales up. But today, we're diving into an approach that refuses to settle, one that promises pure, exact answers.
So what's our mission for this deep dive then?
Well, our mission is to really understand Mourad Sultan Ezouidi's theorem. It's presented as a groundbreaking piece of work that aims to completely redefine how we approach and hopefully solve high-degree polynomials.
Redefine.
Yeah, providing what it claims are exact symbolic solutions, not approximations. We'll even look at a specific demonstration, and it involves an almost unbelievably complex degree 18 polynomial.
Degree 18, wow, okay. Let's get into it. So let's start with the basics, maybe just a quick refresher, though I know many of you listening are already pretty well versed in mathematics.
Good idea.
When we talk about a polynomial, we're essentially talking about an expression, right? Made up of variables and coefficients, combined using only addition, subtraction, multiplication, and these non-negative integer exponents.
That's the core of it.
And the degree of the polynomial, that's simply the highest power of x you see in the equation.
Right, the biggest exponent.
Now, when you hear degree 18 polynomial, you might picture just a jumble of numbers and variables, and you'd be right. It looks messy.
It definitely can look messy.
But what does that really mean for solving it? It means it's historically been a monumental headache.
Oh, absolutely. A huge headache.
We're not talking about a simple quadratic equation, something you can solve with that straightforward formula we all learned.
Not at all. X squared plus bx plus c equals 0. This is way beyond that.
The higher the degree, the exponentially harder it becomes to find those exact roots, those specific values of x that make the equation true, that make it equal 0.
Indeed. And for centuries, mathematicians have really grappled with this. And when classical methods kind of hit a wall, the fallback has almost always been, numerical approximations.
Okay, so things like Newton's method. Is that the kind of thing you mean?
Exactly. Newton's method is a prime example. While it's incredibly powerful and it's widely used in fields like engineering and physics, these methods operate by iteratively getting closer to the answer.
Closer, but not necessarily exactly there.
That's the key point. But here's the inherent problem. They rely on this iterative process, the step-by-step guessing and refining, and they come with the risk of rounding errors.
Okay. Little bits of inaccuracy creeping in.
Precisely. And these aren't just minor annoyances, they accumulate, especially with higher degrees. Each calculation step introduces a tiny bit of imprecision, maybe just rounding off a decimal place way down the line.
All right.
But by the time you're dealing with a degree 18 polynomial, those tiny bits can add up to something significant.
So you can't truly guarantee the exact values anymore.
You really can't. And this stands in stark contrast to the scientific and engineering desire for absolute precision in many applications. Designing a bridge or calculating an orbit.
Yeah, good enough might not be good enough there.
Definitely not. And that brings us to the real historical barrier. This leads us into a really foundational concept in algebra. Abel's theorem. Niels Henrik Abel, 19th century.
Abel's theorem. Right, I remember that name.
It profoundly reshaped our understanding of polynomial solvability. It states quite definitively that there is no general algebraic formula.
No single magic formula, like the quadratic formula.
Exactly. No formula involving only basic arithmetic operations, addition, subtraction, multiplication, division, and roots, like square roots, cube roots, fifth roots, what we call radicals. No general formula using only those tools for solving polynomials of degree 5 or higher.
5 or higher. So not just 18, but anything from degree 5 upwards falls into this category.
In general, yes. That's a pretty definitive statement, fundamentally unsolvable in an exact algebraic way, using only radicals. It's almost like a mathematical brick wall was hit.
So, if I'm understanding this correctly, for a long, long time, this meant that many high-degree polynomials were just considered fundamentally beyond exact solution by algebraic means. They were essentially unsolvable by those traditional radical methods.
That's exactly right.
This isn't just about it being practically difficult, it's like a theoretical speed limit.
Precisely. Abel's theorem didn't just say it was hard to find solutions using radicals. It said, for a general polynomial of degree 5 or higher, you simply cannot express its roots using a finite sequence of these radical operations. This raised a really important question for the mathematical community. If classical algebra, using radicals and even numerical methods, fall short, how can we truly understand the precise behavior of these complex equations? Or do we just have to accept this fundamental limit?
So people just accepted relying on approximations.
For a vast swath of problems, yes. It meant mathematicians accepted reliance on approximations or acknowledged they couldn't write down an exact radical solution for many equations.
But what does this all mean for us today looking at this? It means we've kind of been stuck, right?
Yeah.
Relying on good enough answers for some of the most complex mathematical puzzles, or just admitting defeat on finding exact solutions with standard tools.
It certainly sounds like an accepted limitation.
Until now, that is, or so it seems. Okay, here's where it gets really interesting and where maybe the established wisdom gets a profound challenge.
This is the exciting part.
Mourad Sultan Theorems theorem claims to bypass these very limitations we just talked about. It suggests that even polynomials with radical roots, the kind Abel said were often unsolvable that way, can be solved exactly.
Right, that's the claim. It seems to fly in the face of the implications of Abel's theorem for many cases.
It does. This isn't just some small tweak or an incremental improvement. It feels like a direct challenge to a really long-held mathematical belief. So how does this theorem fundamentally differ in its approach? Especially given what we just discussed about Abel's theorem. Is it truly bypassing that limitation? Or is it fundamentally, rethinking the very nature of what solvable means here?
That's a brilliant question, and it gets right to the heart of the potential paradigm shift. Ezouidi's theorem isn't simply trying to brute force a solution using radicals in some new clever configuration. It's about a completely different philosophy, it seems.
A different philosophy, okay.
It focuses on deriving exact symbolic solutions rather than just numerical approximations.
Symbolic solutions. What does that mean exactly, in contrast to numerical?
Think of symbolic not just as ending up with a number, like 3.14159, but as ending up with an instruction set or a perfect representation. Instead of saying the answer is approximately 3.14159, a symbolic solution gives you the answer is pi.
Ah, okay. The actual thing, not just its decimal value.
Exactly. It's the exact fundamental representation, not just a measurement or an approximation. It's working with the mathematical building blocks themselves, the symbols, the variables, the relationships, not just measuring the final structure numerically.
So this theorem claims to provide these precise, solvable roots, even for polynomials that traditional algebraic methods, because of Abel, would deem unsolvable by radicals.
That's the assertion. It provides precise symbolic forms for the roots. It's not just a numerical recipe.
How does it do that, though? What's the mechanism?
Well, the core of Ezouidi's method involves what's described as a structured recursive process.
Recursive, meaning it loops back on itself somehow.
Sort of, yes. Imagine it like a meticulously crafted set of instructions where each step precisely builds upon the results of the ones before it. It systematically finds the exact values of the roots by essentially breaking down the polynomial into manageable interconnected components.
Okay.
This recursive approach is absolutely key because it means we avoid that accumulation of approximation errors that plagues numerical methods.
Because you're not approximating at each step.
Exactly. Every value derived is exact, it's symbolic, never an approximation, because it's always perfectly constructed from previously known exact symbolic values.
That makes sense. You're preserving the exactness all the way through.
Precisely. If we connect this to the bigger picture, it's about shifting from that iterative guess and check approach where you get closer and closer but maybe never quite hit the bullseye to a direct structural understanding of the polynomial's hidden properties.
Like finding the blueprint. I like that analogy.
Yeah, it's like discovering the blueprint of a complex machine, rather than just poking at it from the outside to see what happens. This method essentially claims to reveal an inherent elegant structure within these seemingly chaotic high-degree equations.
The structure that maybe the traditional numerical methods just They just miss it.
Yeah.
Or can't exploit it.
That seems to be the idea. They're focused on the numerical value, not necessarily the underlying symbolic structure that this theorem apparently taps into.
All right, so let's put this groundbreaking theory, or maybe controversial theory, depending on how you look at it, to the test.
Let's see it in action.
For our deep dive today, we're going to tackle this genuinely intimidating 18th degree polynomial. Now, the full equation is, well, it's incredibly dense and long.
It really is.
It's far too much to just rattle off here without causing some serious listener confusion. But trust me, it's a beast. You can picture it. A long string of x's raised to dizzying powers, from x to the power of 18 all the way down to a constant term with lots of complex coefficients in between.
19 terms in total if you include the constant.
Right. And we've put the full equation in our show notes for anyone who really wants to see the raw complexity firsthand.
Definitely worth a look, just to appreciate the scale.
Traditionally, a polynomial of this magnitude, well, it would send mathematicians running for cover, or at least reaching straight for their approximation algorithms, right?
Absolutely. This is exactly the kind of problem where you typically say, okay, numerical methods it is.
But the brilliance claimed here is how Ezouidi's method supposedly tames it systematically.
Indeed, this particular polynomial, let's call it time px, represents exactly the kind of challenge that Ezouidi's theorem is designed to solve. So the initial steps of applying the theorem, they involve systematically determining a series of symbolic coefficients.
New coefficients.
Yeah, related to the original ones, but derived. The theorem labels these as Serre. These Serre values are calculated based on the original polynomial's coefficients, which we usually call AI, or in this paper's notation, LQ.
Okay, so Serre are derived from LQ.
Correct. The polynomial is then conceptually re-expressed in terms of these new symbolic coefficients. It looks something like this, conceptually. Px isotype by 8, 6 over 17 plus s by 16 plus 3 by 15 plus rho all the way down to 9 plus s 0.
So it still looks like a degree 18 polynomial, but with these SAR things instead of the original numbers.
Structurally, yes. But the key here, and what's potentially revolutionary, is that every single one of these Serre coefficients is determined symbolically.
No approximations allowed.
None whatsoever, at any stage. It's all about working with exact derived expressions based on the original LQ values. This ensures that the foundation we're building upon for the eventual solution is perfectly precise, symbolically speaking.
Okay, let's drill down now into the very heart of Ezouidi's theorem. You mentioned it's based on a recursive process.
Yes, and that process is driven by a core formula.
Right. The claim is that this powerful recursive formula allows us to find these Serre coefficients step by step. Now, we won't throw a jumble of Greek letters and, complex summation signs at you right here.
Probably wise. It can look intimidating.
Yeah, because the power isn't really in memorizing the symbols. It's in understanding its logic, right? How does it achieve this symbolic precision? Can you help us unpack the core mechanism of this formula?
Absolutely. Think of it like a meticulous recipe, maybe, that guarantees an exact outcome every time if you follow it perfectly. This recursive formula, and again, you can see its full mathematical glory in the show notes if you're curious.
For the brave ones among us.
Yes. It dictates how each Serre's coefficient is calculated based on the original coefficients, LQ, and crucially, previously calculated Serre values.
Okay, so what are the ingredients in this recipe?
Well, it combines a few key things. It involves what are called binomial coefficients.
Like from Pascal's triangle, CNK.
Exactly those. C, N, K, N, choose K. They essentially act like a mathematical choreographer here, arranging the terms in the formula and telling us how many ways things can be combined. They ensure the terms are correctly weighted and structured within the sum.
Okay, so combinatorial weights. What else?
The formula also involves a base coefficient from the derived set, Serre or R, which gets adjusted by its power as you work through the recursion. And crucially, it references earlier calculated terms from the Serre family, specifically terms like Sn1.
There's the recursive part. The current calculation depends on previous ones.
Precisely. This highlights the recursive nature. The current Serre terms you're calculating depend directly and exactly on terms that have already been calculated in previous steps of the process.
And because those previous ones were exact?
The current one is also exact. This recursive calculation ensures that we are always working with exact symbolic values. It propagates precision throughout the entire calculation rather than letting errors creep in and accumulate. It's actually a very elegant way to maintain exactness from start to finish.
Yeah, that makes conceptual sense.
Oh, yeah.
But now, here's where it gets really interesting and frankly a bit mind-blowing when you apply it to that degree 18 monster.
Yes, this is where the magic seems to happen.
What's truly remarkable about applying this powerful formula to our specific degree 18 polynomial is how many of those calculated sphere coefficients turn out to be 0.
A surprising number of them, yes.
I mean, think about that complex, incredibly long polynomial we started with. 19 terms, all those different powers of x, each with its own, often large coefficient. But the theorem's calculations, following this recursive formula, for a huge number of those corresponding zero coefficients, specifically zero coefficients all the way through 0
Right, the first 8 of them.
And again, skipping one and going from 0 QR3 to 16.
The last 8 before the final constant term.
They consistently yield 0. Just poof, gone.
It's a dramatic simplification.
It's like a magical cleanup crew went through the equation. All those intermediate terms in our symbolic zero representation, they just vanish.
Which leaves?
We're left with only 2 significant non-zero coefficients in that symbolic form. 0, 2r, and the final one, S17.
The coefficient for the by 9 term and the constant term.
Exactly. And even those, while they represent, numerically large values, the paper shows they simplify to surprisingly clean symbolic forms, elegantly tied to powers of 18.
Yes, the calculations yield S8R, Ixlit's 48619 and S7R 48617 1818. Still exact symbolic values.
This isn't just a simplification, it feels like a revelation of some kind of underlying structure that was completely hidden before.
That's a good way to put it. This outcome dramatically streamlines the polynomial. It really is an elegant manifestation of the theorem's claimed power to distill complexity, to cut through what appears to be an impenetrable thicket of terms.
And it's not a fluke. It comes directly from the formula.
According to the theorem's process, yes. It's the result of the symbolic recursive nature of the theorem at work. It contrasts so sharply with the brute force approach of numerical methods, which would treat every single original coefficient as just an independent value to be approximated and carried through.
Where they wouldn't see this cancellation effect.
Probably not. Ezouidi's theorem instead seems to reveal how these coefficients are inherently linked through this recursive structure, and in this specific case, many of them systematically cancel out, leading to this profound simplification.
Which naturally raises an important question. How does this drastic simplification then lead us to the final exact roots? Especially when, Abel's theorem is still sort of looming in the background saying you can't do that with radicals generally.
Exactly. It's almost like the theorem is peeling away layers of an onion to reveal a much simpler, more manageable core. The question is, what do we do with that core?
So what does this all mean for actually solving our original mathematical monster?
Yeah.
We have this 18th degree polynomial.
Providing what it
And after
claims
applying
are
Ezouidi's theorem and its
exact
incredible
symbolic
simplification,
solutions.
it reduces to something far, far more manageable. What was it again?
The simplified form becomes px by 18 plus s17 plus 7.
By 18 minus a term with by 9 plus a constant term equals 0.
That's it. That's it. All those intermediate terms, from by 17 down by 10 and from by 8 down to x, they all vanished because their corresponding store coefficients calculated to 0.
That is just wow. This really shows the power of working symbolically, discovering that hidden elegance within the complexity, from 19 terms down to just 3.
It's a remarkable reduction, and this simplified form by 18 by 9 plus S17 is where the true mathematical elegance, or perhaps the trick, comes into play for solving it.
How so? It still has a by 18 term, which seems pretty high.
It does, but look at the powers, 18 and 9. Notice that 18 is exactly twice 9.
Okay, I see where you're going.
Right. The structure allows it to be rewritten as a classic quadratic equation if we just make a little substitution. If we consider by 9 as a single variable, let's call it y. So let y apply 9.
Then by 18 would be by 9 2, which is y2.
Exactly. So the equation becomes y2, y plus s17, 0.
And that's just the familiar a2 plus by plus c0 form, where a is 1, b is negative zeta r, and c is SAR.
Precisely. It's a quadratic equation in the variable y, which stands for by 9. And we all know how to solve quadratic equations.
Yeah, using the quadratic formula, mirrored b plus or minus the square root of b squared minus 4ac all over 2a.
That's the one. And critically, we use the exact symbolic values we derived earlier for setar and S17 as our b and c coefficients. Well, imagining setar is b and s is c and a is 1.
So all the inputs to the quadratic formula are exact.
Correct. The paper also details calculating an intermediate value, which it calls S1. This value is calculated as Natchez 8R2 plus 4S17, which looks very much like the discriminant part, P2 4AC, though with a sign flip convention here. from the quadratic formula.
Okay, so that SR is related to the discriminant. And is that value exact too?
Yes, because S8R and S17 are exact symbolic values involving powers of 18. This SR is also an exact symbolic value. The calculation shows it comes out to Natchez 236, 361, 2693, 1818. It's a large negative number, but it's exact.
Got it. So we plug Natchez 8R and S17 and the related discriminant value in the quadratic formula.
And we find the two exact solutions for y. Remember, y is by 9. Because all inputs to the formula were exact symbolic values, the two resulting solutions for by 9 are also exact symbolic expressions.
They might involve square roots of that big S number, I guess.
Yes, they will involve squart, or effectively squart, 23636126931818, which simplifies nicely since 1818 is a perfect square. But the point is, it's still an exact representation involving potentially radicals and the number 18.
Okay, so we have two exact symbolic answers for what by 9 must equal. Now what?
Now comes the final step. We need to find x, not by 9. So we take the 9th root of each of those two solutions for by 9.
The 9th root, okay.
And because we're dealing with potentially complex numbers, since the discriminant calculation suggests the solutions for y might be complex, or we need roots of potentially complex numbers, taking the 9th root will give us 9 distinct complex roots for each of the two solutions for y.
Right, finding roots in the complex plane gives you multiple answers.
Exactly. This is where complex exponentials involving e and pi and I, the imaginary unit, naturally come into play to represent all those different roots spread around the complex plane.
So the final answer isn't just one number, but a set of numbers, 18 of them in total.
Correct. Two sets of 9 roots. The final structure of the roots after all that deconstruction and solving the quadratic and pi looks like this, incorporating those complex roots. XR equals 18 plus 18, Nashware 8619 plus Nashware parrot 2363612693219, E 2 pi r 9.
Okay, that looks complicated, but I see the structure. There's the solution from the quadratic formula involving S8R, which was related to 48693, and the discriminant S8R related to 23636122693. Then you take the 9th root, 19, and you multiply by the complex exponential part, e to power 9, to get all 9 distinct roots as card goes from 0 to 8. And there are two main branches because of the plus 8.
Precisely. That formula represents the complete set of 18 exact symbolic roots for the original polynomial.
That is the exact symbolic root description. Not an approximation, not a guess based on iteration, but a precise mathematically derived answer based on the theorem's process.
That's the critical point being made. Unlike traditional methods, which are often forced to fall back on numerical approximations for something this complex, Ezouidi's theorem, in this case, provides a precise symbolic solution structure.
And this ensures that the roots obtained are exact, not subject to those accumulating rounding errors we talked about.
Correct. This approach fundamentally ensures, according to the theorem, that we can find the roots exactly, even for high-degree polynomials that are considered too complex for classical algebraic methods, using radicals to handle generally, potentially challenging the perceived scope of Abel's limitations.
It really is a testament to the potential power of a novel approach, thinking about the structure differently. So let's zoom out a bit. What does this all mean for the broader world of mathematics, and maybe even beyond?
Well, it's potentially quite significant.
We've just witnessed a method that seems to crack open what many considered a closed book for exact solutions. The sheer elegance of turning that daunting 18th degree polynomial into something solvable using a quadratic-like structure. I mean, that's truly mind-blowing when you think about the initial complexity.
It is quite startling, the degree of simplification achieved.
And the profound insight here isn't just that the polynomial gets simpler numerically. It's that Ezouidi's method seems to reveal an inherent, elegant structure within these apparently chaotic high-degree equations. A structure that, like you said, traditional methods completely miss or just can't exploit.
Right. It suggests there's an underlying order that can be accessed if you use the right symbolic tools, the right recursive perspective.
It's like finding a hidden key, or maybe a hidden pattern, that unlocks a complex safe. It demonstrates that for certain polynomials, perhaps many, even those with radical roots, where Abel's theorem implies difficulty.
We might be able to find exact symbolic solutions using this different approach.
Which seems to directly contradict the long-held implications of Abel's theorem for such cases, or at least refine our understanding of its boundaries.
It certainly prompts a re-examination of what unsolvable by radicals truly encompasses when different symbolic transformation techniques are allowed.
Think about the implications then. Less guesswork, more certainty, even for problems that were previously just thrown into the unsolvable by radicals bucket.
Exactly. What's truly fascinating here is how this theorem doesn't just offer an alternative method, it potentially challenges the very definition or perceived boundary of solvability for polynomials previously deemed impossible to solve exactly using standard algebraic tools.
It's like the limits aren't static.
Exactly. Limits in science and math are often redefined by new ways of seeing the problem, by entirely new theoretical frameworks. Perhaps this is one such framework.
And while this is, deep mathematics, what about the ripple effects? Can advancements like this impact fields outside pure math?
Oh, absolutely. While it might take time for such theoretical advances to percolate into applications, the potential is there. Think about any field that relies on highly precise modeling.
Like physics.
Engineering. Precisely. Designing ultra-precise optical systems, maybe. Predicting the long-term behavior of complex dynamical systems like planetary orbits or protein folding. Even areas like advanced signal processing, control theory, or maybe even certain aspects of cryptography or quantum computing.
Anywhere where tiny errors could have huge consequences down the line.
Exactly. In any situation where precision is absolutely paramount, having access to exact analytical solutions rather than numerical approximations becomes incredibly valuable. It removes a source of potential error and uncertainty.
It really does raise an important question then. What other long-standing mathematical or scientific impossibilities might just be waiting for reevaluation? Waiting for someone to come along with a fresh perspective or a completely new type of theorem.
That's the exciting part about scientific and mathematical progress, isn't it? It makes you wonder, are there other areas where we've accepted limitations based on the current toolkit, where a new symbolic approach might reveal hidden solvability?
It makes you think about how many other solved problems or problems deemed unsolvable might have deeper, more elegant solutions just waiting there if we just challenge our core assumptions about how to approach them.
It's a constant process of questioning and refining our understanding.
This whole journey through this deep dive, it really reveals that even in fields as old and established as mathematics, there are still potentially new frontiers to explore, new exact solutions waiting to be discovered, perhaps.
Absolutely. It's a powerful reminder that our understanding of the universe and the mathematical tools we use to describe it are always evolving. They're not set in stone.
It's quite inspiring, actually.
This journey really underscores that the pursuit of exact solutions, even when faced with perceived impossibility, remains a fundamental driving force for progress. It invites us all, I think, to consider how many other areas we might be settling for are good enough.
When true precision or a deeper understanding might be just waiting for discovery.
Exactly. What's fascinating here is how often these new ideas challenge foundational beliefs, really pushing the boundaries of what we thought was possible in mathematics and science.
And that's our deep dive into Ezouidi's theorem and the fascinating and perhaps newly opened world of high-degree polynomials. We hope this exploration into the possibility of exact solutions has given you a fresh perspective on what might be possible.
We certainly hope you feel a little more well-informed and maybe perhaps even a bit inspired by the ongoing evolution of human knowledge and the power of new ideas.
Until next time, keep digging, keep questioning, and keep deep diving.
Thank you for listening. So this is an example of a degree polynomial equation, and we show you how we derive the exact roots. See you next time, inshallah. We will try to take a practice.